Okay, so welcome to the lecture on metabolism. Think about eating a piece of cake. What happens to it? How does your body break it down? How does your body turn it into energy, and what does it do with that energy? We're also going to talk about enzymes and the importance of enzymes when we discuss metabolism and metabolic rates and metabolic pathways. All right, so what I really want us to focus on during this lecture, during this chapter, is putting it in a perspective of how does our body work. And look at your parents. Look at the genetics you have. Are your parents thin and in shape? You probably have good genetics. You probably have a high metabolic rate. If they're not, then you may not have good genetics and a high metabolic rate or metabolism. Doesn't mean you're stuck. Genetics are not everything. They're a part of the equation. But we also want to think about how do we change our metabolic rate and what's going to happen. I guarantee over time our metabolic rate will decrease. It will decline. It's a natural part of the aging process. But we want to remember what structure plays a key role in producing energy. Hopefully you guys can remember and you're going, oh, I know what that structure is. If not, go back to the chapter on the cells. Who's the powerhouse of the cell? That's the key structure for your metabolism. All right, so that's what we're going to be looking at. That's what we're going to be talking about throughout this chapter, is how this works in our body and how do pathways work and what happens when we disrupt pathways, things like that. All right, so we want to talk about energy. Energy is all around us. Burning prairie grass is a conversion of energy. What we're doing is taking potential energy, or what we call stored energy, and turning it into energy of motion, energy of action. That's kinetic energy, right? So potential turns into kinetic. How good are you at turning potential into kinetic? That's what we want to talk about with metabolism. So think about the Olympics. Here's our bobsled team in the Winter Olympics. They are converting energy from one form to another in order to race. What did they have for breakfast? That is being converted into ATP, energy of action, in order for their muscles to work and their bodies to function to be able to race. Right? Now, my old dog, even at rest, when this boy was laying on the couch, his body was using energy. His heart's beating, his lungs are working, neurons are firing, digestive system's working, all those things. He's using energy. So he's taking what he ate. He's taking the food that was in his stomach, in his digestive system, and converting it over into a different form of energy. So when we talk about energy, whether it's metabolism or a prairie fire or the dog, we're talking about laws of thermodynamics. Now, there are two laws of thermodynamics. Make sure you know these. The first law tells us energy cannot be created or destroyed. It can only be altered in form. Okay, so that's the key with energy. We're just changing its shape, changing its form. We're not creating it. We're not destroying it. We're just turning it into something a little bit different. So light a match. You didn't create energy here with this match. You turned the sulfur in the matchstick, or if you use a cigarette lighter, the gas in the lighter, you turned it into a different form of energy. That's all we do, is we change it and we alter it. Now, as we alter it, or during conversion, all energy, when it's being converted, follows the second law. So, as we convert it, some of the energy is lost as heat. No system is 100% efficient. Oh, that's supposed to be a 100. Okay, no system is 100% efficient during the conversion of energy. Basic rule of law, rule of physics. You change energy from one form to another, Nothing's 100% efficient. This is where we get heat from, our body heat. The heat on your computer right now, the heat on your phone, the heat on your car engine when you drive the car. Those are all following thermodynamics and producing heat because nothing is 100% efficient. The more efficient, the less heat generated. So think about different light bulbs. Some light bulbs get super hot and they're very inefficient. Other light bulbs use less energy, they're more efficient, they don't produce the same amount of heat. There's thermodynamics for you in your light bulbs. Okay, now in living systems, this is the form of energy we focus on. This thing called adenosine triphosphate, or ATP. That's the magic energy all life on Earth ultimately needs. Alright, so ATP. Now what's great about ATP is it's this little sugar phosphate, this little structure here, kind of looks like a house. It has 3 phosphates. 1, 2, 3 phosphates attached to it. And then here is the adenosine, or the base adenine, right there. Now, it's like a loaded mousetrap. Crank it back, got all these 3 phosphates, everything's good, lots of potential energy, it's excited, it's ready to go, and then all of a sudden, BAM! Energy gets released when you break a bond. Snap that bond right there, bust off that phosphate, and energy comes out. That is the energy that drives life. Nerve conduction, muscle contraction, building proteins, your eyes blinking, your fingers moving. It's that energy coming off when that phosphate is broken off. That's what life depends upon. Now the great thing is our body simply rebuilds that molecule. It grabs a free floating phosphate, hopefully you've eaten something with phosphates, and it shoves it back on and reattaches it and resets this structure. We're constantly doing this. Millions and millions of these ATP molecules are needed every single second of the day in order for our body to work. If we lose ATP, we don't survive. So in order to make energy, to do this, we follow a pathway. We go through a series of reactions. And in order to get a reaction to get started, the system needs a thing called the energy of activation. Okay, that's your starting energy. So if you guys turned on your car, that spark that ignited the engine, that got the engine started, that's your energy of activation. That gets the car going. That starts the reaction. Okay, so all systems, all reactions, all pathways have to have a certain amount of energy of activation to get going. So they draw it out. This little graph shows it. It says it's kind of like this big hill here. You got to get up to the top of the hill. You need this energy to get you up there to then get the reaction to proceed. But what we're going to see, this is where the enzymes come into the picture. When you have an enzyme, the enzyme decreases the size of your hill, decreases the energy of activation required. So enzymes lower the minimum energy of activation needed. So you look at the size of your hill here versus your hill here. It's the same reaction, the same pathway. It just happens a lot easier because of an enzyme lowering the energy of activation requirement. All right, so that's a big thing, a big feature we want to keep in mind as we look at pathways. So in our body, if we don't have functional enzymes, that's a bad day for us because our pathways slow down. They go back to needing this huge amount of energy to get started, and it's incredibly difficult for the pathway to even function. It doesn't stop, it just slows down. You know, instead of happening in a matter of seconds, it may take hours or days for that pathway to happen. We can't survive like that. Okay, so anytime we have a pathway in which we're trying to take a large substance is, and break it down. Oh. You're going through what's called degradation. Okay? So a large substance is broken down into smaller substances. The other terms that we probably use that make more sense for most of us: digestion, decay, decomposition, etc. So degradation pathways. These are, again, are these pathways that you start with something big, and there's our degradation. Here's our big substrate, our big ingredient, product, whatever it is, and it fits on a specific enzyme. So notice the little notch in the substrate right there. Notice the notch there. Those two fit together. Specifically, those two things attach, and then the enzyme substrate complex jiggles and jostles and kind of moves around a little bit, and then it pops the substrate apart into smaller products. These are the end products of this particular little pathway. The enzyme's still there. It still works. It functions. And it's good to go again. Keep doing it. Keep breaking things down. So if you've eaten any complex carb today, like starch, your body is breaking it down. Enzymes are necessary to break the starch apart and make it smaller, turn it into smaller and smaller substances. Eventually that starch is broken down into glucose, and the glucose is small enough to actually diffuse into your cell. Alright, so that is our degradation pathway. The exact opposite is called synthesis. Small molecules are added together to form a large molecule. Alright, so a bunch of little ones get combined together, and those guys attach and are pushed together, and they make something bigger. Growth. Building. Etc. Enlargement. What do we want to call it? Those are examples of synthesis pathways. So when your body is putting on muscle mass, you're gaining weight, your hair is getting longer, it's all going through synthesis. So you have a bunch of small substrates that fit together with a specific enzyme. Again, here's the notch, and there's the notch there. They attach, they become the complex, and they jiggle, jostle, and kind of get smashed together, and they form the larger product over here, and the enzyme still remains functional. It goes and does it again and again and again and again. Okay, so synthesis pathway. These pathways are how our body grows and develops and continues to maintain itself through the process of synthesis. But without digestion, we can't get the necessary ingredients and the energy and basically the raw materials to be able to grow and develop. So you think about it. Lunch today gets broken down and rebuilt into new structures for your body and energy production. All right, so anytime an enzyme is attaching to the thing we call the substrate, it goes through what's known as the induced fit model. All right, so they don't fit exactly perfect 100%, but pretty darn close. And the enzyme has this area called the active site. That's just the location that the substrate fits into. So if the substrate happened to be a triangle shape, it wouldn't work with this enzyme. That enzyme is specific to that particular substrate. And that's a big thing to remember about enzymes, that they are specific to the substrate that they work with. And if you don't have the right substrate, they don't work for you. So those combine, come together, and they form this little substrate enzyme complex, and the reaction proceeds very, very quickly at this point. So we'll talk more about that in our next lecture.